Welcome to Practical End-to-End Learning to Rank using Fusion. And my name is Andy Liu, and I'm a senior data engineer at Lucidworks, and I work for the data science and engineering team here. Just a little bit about me and my background. I've been working with search for a pretty long time now, almost 15 years, and started off building websites and search engines, and started off with Lucene first before even Solr came out. As Will was alluding to before, search activates machine learning, and activates AI. So that's kind of my progression too in my career. So naturally, after working with search and taking text really seriously, you kind of move into the next level, which is trying to mine more information and more value out of your text data. So that was definitely the case for me. So did a lot of work in classification, clustering, topic modeling, and of course, when you're dealing with a lot of data, you gotta have frameworks to deal with that data. So also worked with Hadoop and Spark when it finally came out. So worked in a lot of different industries like legal, customer service, e-commerce. So enough about me. Let's talk about learning to rank. We'll be talking about three things today. LTR, what is it? How can I build it? And does it work? A show of hands, how many people have a rough conceptual understanding of what LTR is? Okay, cool. So most of you. Cool. So yeah, I won't spend a ton of time on the conceptual overview, but yeah, like a couple years out of college, I was working for a startup, and we're building a search engine, and everything was great. We were using technologies like Lucene and Nutch, and we had crawled millions of web pages, and everything was going great. One time, my boss calls me into his office, and he's playing around with the search engine, and sure enough, he's looking at a query, and he's like, Andy, I know what the relevant document is for this query, and it's on page 2. You need to go fix this. And I'm like, oh, okay, beautiful engineer. I go back, and I'm like, okay, what about this document can I observe that would make this document go up a couple notches? So like, oh, okay, like I see that maybe increasing the title boost will make that happen, or oh yeah, this document's a little bit newer than all the other documents above it, so maybe I'll boost newer documents. So made a couple of tweaks to the boosts, and everything was great. It was ranked first, and a couple hours later, my boss is like, hey, come in here. Here's another query. This isn't working. This is supposed to be ranked first. Now it's ranked fifth, and so you kind of replay that situation over and over again, and the 20th time I fix the 20th query, but then that ruins the first query, and we're back where we started. And then I was thinking, well, maybe I'll just write a script that will go and run all these searches automatically, and I can keep score of how I'm doing for each of these queries, and from there I can maybe tweak a boost here and there, and then I know exactly what I'm doing and how the tweaking of the boost affects ranking, and that worked. And then after that, I was like, well, maybe I can actually in my script fiddle with the weights automatically, and okay, let's start with the title boost, and let's monotonically increase it until the score keeps going up, and then the moment it goes down, then let's move on to the next boost, and then let's just keep doing that. And that actually worked pretty decently well at the time. What I didn't know was that I had written my first learning to rank algorithm, which was very rudimentary and simple and stupid, but that's essentially what learning to rank is. Conceptually, you're just automatically tuning relevancy, and you're letting an algorithm do it. Even beyond doing something automatically that you had to do manually, I think right now it's pretty exciting because we have some pretty sophisticated models right now that can detect patterns in your data that you couldn't really detect on your own. So it's not just about saving time and saving effort. It's also about being able to have a scoring model that performs way better than what you can get when you're tuning things by hand. So just a quick example. Say I've indexed these documents at the top, and I do perform a process called feature extraction, which is basically just trying to characterize these query document pairs in a way numerically that an algorithm can go and process it. So the features that you might extract would look very close to the relevancy factors that I was just alluding to. The TF-IDF between the query and title, and so on. And I need relevance grades for each of these query document pairs. And I got those from my boss when I was working at that company. But you need a sense for what the right answers are, and we call that ground truth. So the idea is to train a learning to rank model using ground truth in order to produce a model that can rank new queries where we do not know what the right ordering is, and to be able to produce that in an optimal fashion. Incidentally, this is an example of a pointwise LTR model, and there are a couple others, pairwise and listwise, which tend to perform better, but I won't go into too much detail about that right now. So what are the raw materials needed for LTR? So you need documents, you need ground truth, and you need features. Ground truth is pretty straightforward, but let's talk about ground truth. You can obtain ground truth in a couple of ways. You can get them manually, or you can get them implicitly. So manual labels are, you need some experts. So you present experts with a query and a set of possible relevant responses. And it's up to the expert to grade each of the responses. Is this relevant to the query? And on a scale from 1 to 5 or 1 to 10 or whatever. And as you can imagine, they can be expensive to obtain and maintain. And a lot of times you end up with too few examples to really have enough data to train an LTR model. But on the flip side, they can be more accurate, or at least they're viewed as more accurate. Although I would argue that they're difficult to maintain, and a lot of times preferences change over time. So it depends on the domain. Like, it may be impossible to have like a very up-to-date, manually curated list of ground truth labels. And the alternative is using implicit labeling. So really looking at user behavior in your search engine or your search application. So looking at, if you're in e-commerce, looking at clicks, add to carts, purchases. So if a user searches for iPad and clicks on the third response and adds to cart and purchases it, chances are that third response is probably really relevant to the query iPad. So at that point, you're allowing the users to vote and tell you what the relevant documents are. And the nice thing is that they're voluminous, they're cheap. The downside is that they can be noisy, and people can kind of have stray clicks, and you just need to be able to handle those in a good way. So there are a lot of methods in the literature or in the industry that allow you to alleviate that noise through click models. What are some features that you can add to an LTR model? Again, content-based features, maybe document statistics, the age of the document, the length of the document. You can analyze the link graph, use PageRank, and that could be a feature. And there are historical signal-based features, so looking at previous clicks. So the probability that somebody's going to click this document given this query. We're going to look at these kinds of features in a lot more detail because they tend to be pretty informative, especially in certain domains. This is by means not exhaustive. I mean, I just kind of threw out a bunch of different examples. So how can we build it? And so in explaining how we can build an LTR model, I'm going to walk us through a prototype of an LTR model using real data. So what are the high-level steps? First, we're going to index the data set. And second, we're going to configure the LTR features. Third, we're going to extract the features and train a model using XGBoost. So if you're not familiar with XGBoost, it's just a library for gradient boosting. It's a certain class of machine learning models. And then fourth, we're going to deploy the model for query time re-ranking in preparation for production. So a little bit about this data set. I'm using the Best Buy e-commerce data set, and this was released as part of a Kaggle competition some years back. And there's a product catalog with over 1 million items with a bunch of different metadata fields. And again, those aren't all of them. That's just a sample of them. And click signals over a 2-month period, which is really great data to work with. Over 3 million clicks. So just to give you a sample of what this looks like. So here are some sample products. You have an iPad 2 and 32-inch TVs. So this is from a while ago. And click signals. Just pretty much a flat list of click events. So each click event will have a query and a doc ID and a timestamp. So if you look at the first row, this indicates that a user searched for LCD TV and clicked on that document when searching for that search term. So what are we going to use as ground truth? So we're going to use implicit labels, and we're going to use the click signals as labels. And in particular, we're going to aggregate them by query and doc ID. So again, the same caveats about there can be noise in this data, but at the same time, people don't click on things at random. So there is a good amount of information to be mined out of this data. And again, use a click model if you have the data. This particular data set did not have the data required to train a click model. But basically what we're doing is we're just allowing the users to vote with their clicks. And if you have enough data, then you could be a little bit more confident about users' preferences. So at the end of the day, we're going to have query, doc ID pairs, and a certain weight. And that's just basically the number of votes that document got for that query. Yes?
There's no correction for what rank the result came in? People are more likely to click on the first result than the fifth result.
Absolutely. Yeah, so there is not right now because we didn't have the data to be able to do that. So that's the click model that I was alluding to. So a lot of these click models factor that in. And actually, Fusion actually comes with a click model. So if you have all the data in Fusion, so you just need skips and as well as clicks, then Fusion can actually generate ground truth that adjusts for ranking bias and position bias. So in this particular model, here are some of those features that I use. Content-based features. You've heard of those. Document statistics, so average customer review of the product, the number of customer reviews, the price of the product. Statistics about the query, so the popularity of the query. So this is actually a pretty informative, ends up being a pretty informative feature. I'm going to talk about this a little bit more later. The number of characters in the query, and as far as historical signal-based queries, I added a query intent feature, which is derived from click data, but it's basically just going to predict the query category of the query coming in. So the query is iPad, it's going to predict that it's a tablet. And the feature is basically, hey, does a candidate document and have the same category as the category that I detected? Yes?
Sorry, I'm going to ask another basic question here.
Sure.
So you're using TF-IDF, but suppose you have something like a query like Nikon SLR. Do you really want to be basing the results on the IDF of Nikon versus some other brand? Their catalog may be 1,000 times bigger. Should they be downgraded for that?
Can you repeat that question? So Nikon is a commonly used term.
Nikon, let's say Nikon SLR. Search for Nikon SLR. Let's suppose there's some other brand, Chang SLR, and Chang has one model of SLR and Nikon has 100 models of SLR.
Yeah.
Then the IDF of Nikon is going to be 100, so the IDF of Chang is going to be 1.
Sure.
Right? So you're going to be downgrading something. I'm just asking why you're only using TF-IDF here and not just, why isn't, let's say, binary presence of the term not corrected by IDF among the possible?
Yeah, you can do that, and you absolutely can. I mean, the downside of doing that is that you might blow out your feature space, so you have a model that's a lot more difficult to train. But yeah, I mean, depending on your domain, you may want something like that. So you may perhaps, you want to extract out your IDF weights as a feature that you want to learn. I would say, in other domains, you would want something like that. You want IDF to do its work. Right. So absolutely, some of this is domain specific, and it depends on what you would want to do. I mean, maybe you want to pull out some features as one-hot encoded, or some words as one-hot encoded, and let the model figure that out. But in general, you don't want to go too overboard with that, unless you're Google. I'm sorry. Can you say it a little louder?
You use the query underscore s, right? Full string.
Yes.
The token query underscore t.
Am I tokenizing the query? Is that what you're asking?
The way signals were ranked were by string instead of token. It was the reason on a previous slide.
I'm sorry, I can't make out exactly where you're at. Come see me afterwards. Yeah, thanks. So also we're going to do back to historical signal-based features. We're going to use signal boost from aggregated clicks. I'm going to explain that in right now. So Fusion has a feature called signals and aggregation, and it's Fusion's way of utilizing user behavior to improve search relevancy. And there's a lot to it, but let me just try to simplify things. And let's just go through a workflow of what happens when you're using signal boosting within a single query. So say the user searches for LCD TV, and Fusion searches what we call the signals aggregation collection. And this is basically populated by a job that aggregates all raw signals by query and doc ID and assigns each a weight. And it's going to have a time decay factor, so that clicks that occurred a couple months ago won't be worth as much as clicks from last week. And so when you make this query to the signals aggregation collection, you're going to it's going to return doc ID weights, and it's going to roll those up, and then it's going to query the main collection with boosts applied to each of those documents returned in that signals call. So basically, it's just it's just boosting documents that have been clicked more frequently for a certain query or queries that are similar to the current query. Right now in Fusion, all these boosts have to be hand-tuned. So it comes with sensible defaults, which is the result of a lot of work in the field by our field engineers. And but again, sometimes you want to tweak things, and that's a lot of work. So instead of relying on hand-tuned weights, let's include them as features in our LTR model and see if the LTR model can weight them automatically. So perhaps some of you have seen a problem here. I've mentioned using clicks both as features and as labels. So what happens if you use labels as a feature in a model? So you're going to get a model that achieves 100% cross-validation accuracy that has like zero capability of generalizing to real-life data. So how do we fix that? So the solution is to hold out most recent clicks. So what I did was for this data set, I held out clicks on the last day to use as ground truth. And all the clicks prior to that day I used for the signal-based feature. So this is actually a pretty standard way of training models which use historical data for both labels and as features. Sure.
What is the other signals than clicks?
Right now, we only have clicks for this particular data set. So in a real scenario, you're going to have other signals like, add to carts or purchases in an e-commerce domain. But other domains, you might have some other things like dwell time and some notion of conversion. So. Ground truth. So ground truth is basically it's basically a list of all the queries for which we know what the relevant documents are. So this is sort of like the standard way that we train a supervised learning problem. So we need examples, and we need labels for those examples, and then the algorithm learns the model based on the data. So we're just calling that ground truth. I think that's sort of like an information retrieval kind of terminology, but yeah, it's just basically your label training set. So how are we doing on time? Okay. When does this end? Okay, all right. I gotta speed up here. So basically I'm time bucketing this feature too. So the idea here is that not all clicks are created equal. So perhaps more recent clicks are worth more than clicks from a long time ago. So let's see if I can bucket them and let the algorithm sort that out. And just to kind of illustrate this intuition, here's plots of click volume per day for the query GPS, and here are plots for each for the clicks, the number of clicks per day for that product. And the only thing that to note here is that the most clicked document on the top stops getting clicked as time goes on. And if you don't pay attention to time, then your feature is going to boost this document the highest all the time. So it's good to try to tease out which clicks are the most relevant based on when it happened. So how do we calculate these features? We can use Solr's LTR components. So Solr's LTR component makes it really easy to extract content-based features. If you want to learn more about this, there's plenty of docs about how to do this. The one thing that's a little bit different is that we're also using Fusion to calculate features as well. So in a future version of Fusion, we're going to make it super easy to include all the different components that we have as query pipeline stages as features in an LTR model. So things like signal boosting, tail query rewriting, query intent classification, NLP, rules engine. We're going to have TensorFlow integration in the next release, and support for different sidecar collection calls. So you have a collection and you want to fast it over that collection and include those as features. So Fusion makes that super easy to do that. You can script things in JavaScript so you can iterate really quickly on new features that you want to add to your model. And what it does is just simply overlays the features pseudo field with features calculated in the query pipeline stage. And as far as production query time re-ranking, we just we deploy the XGBoost model to the blob store and add a learning to rank query pipeline stage that references that blob, and it's going to go and re-rank documents as according to the model that we trained. I'm going to skip this. This is kind of a redundant slide. So how do we use Solr LTR and Fusion together? So the Solr LTR component is great, but feature engineering is hard. So Solr LTR component makes it really easy to do the content-based features, as I mentioned, but some of these more complex features take a lot of engineering, a lot of work. So Fusion can help fill this feature engineering gap. So our intent is not to replace Solr's LTR component. It's awesome. It works really great. But on the other hand, we do want to try to make all of our expertise and all the existing components available for you to use in an LTR model. So yeah, maybe for simple LTR models, Solr LTR might be good enough, but for more complex and accurate models, using Fusion will make it really easy to add these complex features in addition to what Solr LTR can already do. So analysis of results, does it work? Here's the fun part. So train the model, some stats. There were about 12,000 unique queries in my ground truth sets, producing about 1 million query document pairs, and I extracted 25 different features. The training procedure, I extracted features for all the queries in the ground truth set, and standard cross-validation, and the metric I used is average NDCG at positions 1, 3, and 5, weighted by query volume. The different models I evaluated were XGBoost, which is a pairwise model, logistic regression, and random forest. These are just simple pointwise models just to kind of give you a frame of reference. And then I also trained models with and without signal features, again, for comparison. Some other baselines, so kind of super simple BM25 ranking using a single text field. That's we should always do better than that. Another baseline I used was just taking the signal boost feature and just sorting results by that alone, not even looking at content, which is actually kind of a way that people do this, especially for domains where there's this long tail distribution where you have really popular queries that compose most of your query volume. So just looking at clicks alone actually gets you pretty far in those sort of domains like e-commerce. And another baseline is using BM25 plus hand-tuned signal boost. So this is what you get with Fusion out of the box right now. So here are a list of results. Hopefully people in the back can read read this. It's a little bit small, but I sorted this table by model performance, and the first row is the baseline simple Solr, which is NDCG at 5 of 0.07, and hopefully we're going to do better than that. So the next three are LTR models trained without signal features. So we're starting to get better. So 0.31, 0.39, 0.43 when we're using XGBoost without signal features. The baseline signal boost sort, we're at 0.47, so it actually does pretty well in this particular data set. And using Fusion plus signals, so this is a hand-tuned model, not an LTR model, but it does better than the baseline signal sort. And then we move into our LTR models that we trained using all the features, including the signals features. And as you can see, XGBoost comes out at top with NDCG at 5 of 0.58, which is a pretty significant margin. This is pretty much the same slide, except I did the difference between the models and this signal boost sort. So one good way of analyzing accuracy metrics is to bucket your queries by popularity, and especially in these domains where you have a head-tail distribution of queries. So head queries tend to be easier to rank because there is enough historical click data for signal boosting to be quite effective. For torso and tail queries, signal boosting features will be more noisy because there's not enough data to make accurate predictions. So if we rank all the queries by volume, bucket by percentile, as expected, the vast majority of the individual searches occur in the top 0 to 10%. And let's take a look at the accuracy metrics when we bucket by percentile. So a couple things to point out. So for baseline Solr search, you can see that NDCG improves as you move from head to tail. So this kind of makes sense because this is a content-only scoring model. So tail queries are, by definition, rare queries where users tend to query for very specific things like, blue iPod for my daughter, where textual matching is more important. So, and head queries tend to be more general and popular queries where many products are returned that are textually relevant but need other factors like signals to improve ranking. For the baseline signal boost sort, you see the opposite effect. So head queries perform pretty well, but then they drop off dramatically as you move toward the tail. So for those of you who can't see, the head queries, you're at 0.60, so, and then at the end of the tail, you're at 0.29. The drop-off is true for other LTR models, but for XGBoost, you see much more an improvement in tail queries over the signal boost sort. So you can see that XGBoost is able to kind of do to properly blend between content features and signal features to kind of get the best of both worlds. So, so for tail queries, it's probably going to let off the gas on the signal-based features, and then the content features will take over at that point. Again, here's the difference between all the models and the signal boost sort, but you can see that the amount of improvement is a lot more on the tail side than, but there is still a significant improvement on hedge queries as well. So one nice thing that you get from training an LTR model like this is that most models have a way of revealing which features are most important in the model. So here's a plot of the most informative features in the XGBoost model that I trained. So you can see that the most important features are query popularity, the signal boost feature, and the TF-IDF textual match feature, the query intent feature. So one really interesting thing to note here is that you can't really tell from this plot, but if you actually look at the decision trees in the XGBoost model, you'll see that query popularity is commonly used in conjunction with the signal boost and the TF-IDF features. So again, it's actually learning the relationship between these two features, and under certain circumstances, using the signal boost feature more, and other circumstances, using the signal boost feature less. So this is kind of the kinds of patterns that these more sophisticated models can learn, and that gives you kind of the extra performance boost that we all want. So with that, let me just do a quick demo. Again, how are we doing on time? Let me see. 2 minutes left. All right. All right. This is going to be quick. This is going to be a quick demo. All righty. So here's what a query pipeline looks like. So on the left side are all these different stages, and you can see that there are certain stages like fetch from the signals aggregation collection, as I was illustrating before, and then different fetches for signals from a week ago, a day ago. I'm sure you're going to have tons of questions, and feel free to come to me afterwards and ask me about these things. But here's a stage that extracts query length features, and in JavaScript, so you can iterate pretty quickly, and the API for doing these kinds of things are pretty simple and straightforward. So you're just going to iterate through the documents and the response and add a feature that you calculated over here using, I use the string tokenizer to count the number of tokens. And then, so the nice thing about the query workbench is that you can kind of preview what these queries look like. So I execute a search iPad, and here's the features pseudo field, which is a combination of the Solr LTR features and the features that Fusion is adding, overlaying on top. Here's the whole blob. And right now, I've disabled the learning to rank stage, but right now I'll just enable it. And you can see that it actually works, yay. And let's try a query like, Beverly Hills Cop. So it's great. The movie comes up on top. You see, without the learning to rank, I don't know why this keeps floating. It's like has a mind of its own. If I turn it off, Beverly Hills 90210 is the first result, which is obviously not the right answer. I love 90210, but that's not what I was looking for. But this is what I was talking about. It's a tail query, and it's probably matching the Beverly Hills portion of it in the signals aggregation collection and boosting Beverly Hills 90210 because it's a little bit more popular than Beverly Hills COP. So I can show more examples like this, and well, let's see. We could do the GPS example again. But yeah, I mean, you'll see that if I turn on the learning to rank, oh my gosh, this has a mind of its own. Holy cow. This is what I get for using this Windows laptop over here. But if I turn that on, yeah, you'll see that it re-ranked according to what was more popular recently than what was popular over all time. So I think I'm out of time, but if you guys have questions, feel free to come on by and ask. But that's it. Thanks for coming.